So let us continue our discussion on semi-classical approximation. In which we were focusing on the WKB approach, or to be precise JWKB approximation. We already discussed a few things, and we basically defined something which we called the classical local momentum, which was defined in the following way, that p square as a function of x was 2m times total energy minus the potential energy. And we also defined the local de Broglie wavelength, which was defined as lambda of x is equal to h by p of x, or 2 pi h slash by p of x. And we also had seen that in this approach, the Schrodinger equation takes the form p operator squared psi of x is equal to p square x as a function psi of x. Although this looks like an eigenvalue equation, this is close to being an eigenvalue equation, but it is not an eigenvalue equation because this does not represent that the left hand side is proportional to psi of x. It is not proportional to psi of x because p square x is just not a number, it's a function. And then what we did is that we spoke about the wave function in the WKB approximation, which will take the following form: capital psi of xt, we wrote it as square root rho as a function of xt into e to the power I by h slash s as a function of xt. And this is basically nothing but the typical form of a WKB wave function. That's what we had seen. And you can actually see from this expression itself that the norm squared of psi gives rho, and because if you take psi star psi, then it only gives us rho because the phase part e to the power I by h slash s cancels when you take the complex conjugate and multiply with psi. And also you recall that the current J was given by rho gradient of S divided by M. So we identify the current which is perpendicular to the surface of constant phase S, which is there in this exponential. So finally we also recall that the semi-classical approximation will hold if the de Broglie wavelength lambda is much less than some length scale that is already there in your problem, and lambda is slowly varying with position. So this particular thing was thought of as the limit h going to 0. So these were the two important criteria that we tried to follow when we studied the basics of the WKB approximation in the previous class. Now let us briefly discuss about the approximation procedure or approximation scheme. So let us first think about our aim. We recall that our aim here is to find approximate solutions for the wave function that solves the time independent Schrodinger equation in one dimension. So far we actually had discussed everything in general. We discussed everything in 3 dimensions, but now I am saying that our aim is to study approximate solutions of the, or actually for the wave function, so this is represented by small psi of x, which solves the time independent Schrodinger equation. TISE means time independent Schrodinger equation in one dimension. So we start everything, or we basically started everything in the most general form. Now I am saying that let us look at the problem where we are looking for the solution for the wave function psi x, which solves the time independent Schrodinger equation in one dimension. And also here we recall that we actually had used a polar decomposition of the wave function where we wrote this psi of xt as square root rho as a function of x and t into a phase factor e to the I by h slash s as a function of x and t. Now I am claiming that it will be easier to set the approximation scheme using a single complex function. So let me explain, let me write before I explain this thing. So I am saying that from this, since I am writing the solution for the time independent Schrodinger equation, the time part has been taken care of, e to the power minus iet by h slash is there. So we are just looking at the psi wave function as a function of x only, and I am claiming that I can write it as e to the power I by h slash s as a function of x. Now immediately you can actually raise your concern and say that wave functions are not merely phases. We have seen wave functions having different amplitudes, but here the amplitude rho is always 1. So why should I be bothered about a very specific phase factor only, which I have written here as psi of x? But this objection can be overruled by saying that we can always think of this s of x as a complex function. So my s of x now belongs to complex space. So this s of x is a complex function, and if s of x is complex, then the imaginary part will provide the norm of the wave function. It is always possible to do that. Any row in here in this expression, any row in this expression can be written as the exponential of the log of something and can be brought into the exponent I by h slash s of xt. It is always possible to do that without any loss of generality. So This is therefore what we are going to choose for our discussion, where this Sx, this phase factor, now can be complex function. So let us then write the Schrodinger equation with this psi of x. So we had minus h slash square by 2m d2 dx2 e to the power I by h slash s of x is equal to e minus v of x e to the power I by h slash s of x. So this is my Schrodinger equation, and if I multiply both sides by twice m, then the right hand side is nothing but p square of x e to the power I by h slash s of x, and this remains minus h bar squared d2 dx2 e to the power I by h bar s of x. This I am able to write it simply because by definition classical momentum as a function of x, we can always write it as 2m time e minus v of x. So this is what we have used here. Now immediately I know what this second derivative of this exponential function is going to give me. So because this is a second derivative, so first single derivative when acted upon e to the power I by h slash s of x will give 1 I by h slash and then s prime x. So that when again derived with respect to s will give me I by h slash s double prime of x, and then I by h slash s prime of x will be multiplied twice. So this will be I by h slash s prime of x whole square, and of course there will be this whole phase factor sitting outside, but that will be cancelled with this e to the power I by h on the right hand side. So this is nothing but p square of x. So now I have this equation minus I h bar s double prime of x plus s prime of x whole square equal to p square of x. It looks simple, but is it really simple? Because if we look at this expression of the Schrodinger equation carefully, this is basically nothing but the Schrodinger equation. So if we look at this expression, this equation carefully, the first thing you note is that this is a nonlinear differential equation. Nonlinear differential equation. Why nonlinear? This is nonlinear simply because we have the derivative of s and that squared, this s prime of x squared is there. So it is a nonlinear equation. Schrodinger equation, on the other hand, if you remember, was originally a second order linear differential equation. But here in this equation we have obtained a nonlinear equation. If therefore we have one solution for s and we have another solution for s, we simply cannot superpose them and say that this is another new solution. It is not possible simply because this is not a linear equation, linear differential equation. And why did this happen? This happened simply because we put everything in the exponential. We did not have any other magnitude factor in front. We have all the dependencies in this e to the power I by h slash s as a function of x, where s can be complex. When double derivative is taken on the exponential function, we always get a term with double derivative and a term with single derivative squared. That is what is the property of the exponential function. There is nothing much that one can do about this problem. However, it still can be helpful and it is also manageable. The nonlinear equation actually gives you some idea and it allows you to set up an approximation scheme in which the h bar is can be considered small, and thus the term involving s double prime, you look at this term where we have one h bar as well as we have this s double prime. So this nonlinear equation actually can be helpful in the way that we can choose h prime to be considered as small, and thus the term involving s double prime, this first term, is small. So the claim here, the claim that you can make here is I h bar s double prime is small when v of x is slowly varying. So this is a very important claim that I am talking about. So to understand this, let us consider a constant potential. Suppose I took a constant potential v of x equal to v0, which is nothing but a constant. Suppose, okay. So this is of course the extreme case of a slowly varying potential. Nothing is actually varying in this example, but let us take this as a starting point. Then what is my classical momentum? Classical local momentum is 2m times e minus v naught square root. And also here we see that since my v is a constant, v of x is v naught, the whole quantity here is a constant and the momentum also is a constant, which I denote by p naught. Now what actually do we have in this scenario? Vx is a constant denoted by v naught. So we have basically a particle which is free particle. So the solution of the Schrodinger equation that we know in general for a free particle, we know what the free particle wave function is, and that is nothing but e to the power, apart from all those factors in front, I by h slash p naught into x. This is basically the free particle wave function. So you take this, and also you remember that this is the equation with which we had started, which is e to the power I by h bar into s of x. So if you compare this with the free particle wave function, then immediately we will get s of x must be equal to p naught times x. So this is by comparing with s of x, with psi of x equal to e to the power I by h bar s of x. So if you compare the free particle wave function with this expression, then whatever factor is there in the exponential in this expression of free particle wave function, that means p naught times x, whatever terms are there instead of I by h slash, that is my s of x. So s of x is therefore p naught times x. But then it also tells you what is your s prime of x. S prime of x is simply P naught, and P naught being a constant will immediately tell you that S double prime of x is equal to 0. So we can see that this equation which I have written here, let me put some number to this equation. Let me call this as equation number 1. So this equation number 1, this implies S prime of x whole square minus I h bar S double prime of x equal to P square of x. This equation we can see that is trivially satisfied by this choice of Sx that we have chosen here. How? This is simply because we have just seen that S double prime x is 0. So this term goes to 0, and S prime of x is P0. So P0 squared, and also P we have seen is nothing but P0. Therefore P0 square equal to P0 square. This is trivially satisfied. So we can clearly claim that when the potential is constant, the term I h slash S double prime plays no role at all. It is 0. When the potential is constant, then the term I h bar S double prime is 0. Therefore, it can be claimed that this term I h bar S double prime should be small for slowly varying Vx. This implies I h bar S double prime should be small for slowly varying potentials V of x. Of course, it is not expected that when the term S double prime is 0 for a constant potential, it will be very big suddenly if we vary V slowly or very infinitesimally. So it is generally not going to happen. So it is clear that the term I h bar S double prime is very small when the potential is slowly varying. Therefore, this can be very well implemented by considering h bar going to 0 limit. This is what is basically meant by saying I h bar S double prime is small. This is alternative way of saying that the term I h bar S double prime is small. As h bar goes to 0, which makes in turn the local de Broglie wavelength go to 0, and in that case the potential looks constant to the quantum particle. So as we treat h bar as a small parameter, because we are always treating this quantity h bar, which is Planck's constant, then we are treating h bar as a small parameter, and what we do is that we expand this phase factor S of x in h bar. That means we write this as S of x equal to S0 of x plus h bar S1 of x. S1 of x is the first correction, plus h bar square S2 of x, S2 of x is the second correction, and so on and so forth, and then there will be higher order terms. Now we look one thing. We have already said that S of x has to be the dimension of angular momentum because it has to be the unit of h bar. It has to have the unit of h bar. It cannot be anything else because the exponential I by h bar into s should be a dimensionless quantity, and h bar has some dimension, and that dimension is the dimension of angular momentum. So s, which basically is equivalent to the action, which I have not told you so far, by the way, but you can see, or you can later on encounter this thing if you go to path integral formalism. This s is basically equivalent to the action. So this s we already know has to have the unit of h bar. Therefore this s naught x will have the unit of h bar. There is no doubt about that. But now we are not expanding in terms of some small parameter which is dimensionless. Earlier in our perturbation theory discussions, we were expanding this using the small parameter lambda, which was dimensionless. But here in the second term we can see that there is already one h bar sitting here. So this object, this first correction S1x, should be having no unit. It must be a dimensionless quantity. On the other hand, in the second term we see that already there is h slash square sitting on, so S2x must have the unit of 1 by h bar or h bar inverse. So each of these S0, S1, S2, Sn will have a different unit. That is another important point that you should note. Now let us actually plug this thing into the nonlinear equation which I had written here, equation number 1. So let us call this 2 and we plug 2 into 1. If we do that, then let us look at this expression. We have s prime of x whole square. So let me write that s prime of x means s0 prime of x plus h bar s1 prime of x plus h bar squared s2 prime of x dot 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 whole square. This is s prime squared, and then I have minus I h bar s double prime. So I will write this as minus I h bar s double prime means s0 double prime of x plus h bar s1 double prime of x plus h bar square s2 double prime of x equal to p square of x. So this is the equation. Now we give the same argument as we had given when we discussed the perturbation theory technique. The left hand side here is a power series expansion in h bar, and just as we argued for the parameter lambda in the time independent perturbation theory discussion, here we want the left hand side to vanish for all values of h bar, because I can actually write this as minus p square of x equal to 0. Therefore the left hand side, all the coefficients of h bar should be individually 0, and therefore we thus basically sort the left hand side terms, neglecting order h bar square or even higher order terms. So if we just sort these terms separately, then we can see that there are terms like s0 prime whole square plus from this whole square there will be another term which will be of order h prime, that is the product of these two terms. So this is 2 h bar s0 prime s1 prime. Then there will be all the higher order in h bar orders, so that does not bother us. Then from the second term I will only have I h bar s0 double prime and then minus p square of x plus higher order in h bar squared and higher. So I can write this as s0 prime whole square minus p square of x plus, let me take h bar common, we have 2 s0 prime s1 prime minus I times s0 double prime plus order h bar squared equal to 0. So this immediately gives us, let us call, two different equations. This equation 3 immediately gives us two different equations, one for the coefficients of h bar to the power 0 and another for the coefficients of h bar. So if we equate the coefficients of h bar to the power 0 from both the sides, we will have one equation which looks like s0 prime whole square minus p square of x equal to 0. Let us call this equation 4. And the second one is 2 s0 prime s1 prime minus I s0 double prime equal to 0. Now since we wrote this in terms of s0 double prime and s0 prime, and s0 prime can be solved from equation 4, I will write s1 prime in terms of the s0 prime and s0 double prime as I by 2 s0 double prime by s0 prime. So this is equation number 5. Now the first equation, that is equation number 4 here, one can solve very easily. So equation 4, let me write as s0 prime as plus or minus p of x. This therefore implies s0 of x equal to plus minus p of x prime dx prime, and integrated the upper limit should be x, because I know that I have to get the left hand side as s0 as a function of x, so the upper limit should be x. So integration is up to x such that we get s0 as a function of x. But we know that we are getting this solution of s0 by solving the first order differential equation which we have written here. Since it is a first order differential equation, it must have some constant of integration, so which should be therefore the lower limit, and let us denote that by x naught. So this is all very easy. We have written down the solution s naught of x, and you can also immediately see that our p of x is known. So if you know the energy of the particle, then P of x is completely known, and therefore we know exactly what this S0x is, because P of x is known given the energy is known. So S0x we have figured it out. Now let us look at equation number 5, which is S1 prime equal to I by 2 S0 double prime by S0 prime. But we have just solved for S0, so we have the solutions here for S0 of x. So I know that if S0 of x is plus minus px prime dx prime, then S0 prime should simply be plus minus p of x, and S0 double prime should be plus minus p prime of x. So this is what we obtain from equation number 6. P prime of x divided by plus or minus p of x. The plus minus sign does not bother us simply because this plus minus sign cancels from the numerator and the denominator. What remains is I by 2 p prime x by p of x, but this I can always write as I by 2, then this is nothing but dp dx into 1 by px. So dp by p we can always write log of p, so this is log of px prime. So therefore I also have the solution from S1. S1 therefore is nothing but I by 2 log of px plus some constant of integration. So let us now reconstruct the wave function to this order, meaning to this hbar order of approximation. So remember, so to reconstruct, recall the starting point. We have started our journey with this form e to the power I by h bar s of x, and then we expanded this s of x and we have e to the I by h bar s0 of x plus h bar s1 of x plus higher orders in h. So I can break this exponential as e to the power I by h bar s naught of x into e to the power, this h bar gets cancelled. I have I times s1, but s1 I have the solution here, which is nothing but I by 2 log of px plus some constant c. So this we can write as e to the I by h bar s naught e to the power I into I will give me minus 1, so minus half log px plus c minus half log px plus some I into c, which is again a constant. So this can be written as e to the I by h bar s naught e to the minus log square root of px into e to the power some constant, say c bar. Therefore it is very easy to write psi of x as, since I have e to the minus log of square root p of x, so I will write it as some constant a divided by square root p of x, and then e to the power s naught I know is plus or minus px prime dx prime. So I will write it as plus minus I by h bar p x prime dx prime integration from x0 to x. So this is what we have obtained after this much of deliberations. So this is the basic WKB approximation. So this is the basic WKB or JWKB approximation. So here we have this amplitude a by square root p of x. So that amplitude part comes back here, which we were worried about at the beginning. We did begin with what looked like a pure phase, which is e to the power I by h bar into s of x. So our starting point was just looking like a pure phase, unless otherwise I have told you that s of x belongs to some complex number. And indeed, we have seen that S0 was real, but S1 was imaginary. So with S1 imaginary, the role of S1 was to provide this magnitude part, this amplitude part. So we have actually obtained this expression for the WKB wave function. So with this basic WKB approximation, we note two important things at the same time. We note that probability density, which is nothing but rho, which is psi star of x into psi of x, you can calculate this. And if you take psi star of this whole object, the phase factor immediately cancels. What remains is mod of a square divided by p of x. But then classically I can always write this as mod of x square by m times v of x, where v of x, as defined in the previous class, is nothing but the classical velocity, local classical velocity. And also you note from this expression only that rho x is higher when Vx is small. Why is that? This is simple to explain. As the particle stays more time in a region where V is less, the probability of finding the particle increases. That's what this tells you. Now we also want to mention another point, that recall that in the language of the polar decomposition, when we had written psi of xt as square root rho xt e to the power I by h bar into sxt, there we defined the probability current as rho gradient of s divided by m. We have proved this in the previous class. So if we are in one dimensional scenario, then this is rho by m del s del x, where s of x we know is nothing but x0 to x p x prime dx prime. So we just use this result that j of x is nothing but mod a square by p of x, which we have used from this expression, into 1 by m into p of x, because s of x is given by integral p of x prime dx prime, the upper limit being x. So if you calculate del s del x, I will get 1 p of x, and this p of x fortunately will get cancelled. Why fortunately? Simply because I want this to be a constant. Why do I want this to be a constant? Because it is, if it is not a constant, suppose J of x really is some position dependent current, then it would have violated the conservation law, the conservation equation, which is nothing but del rho del t plus divergence of J equal to 0. This would have been violated. That means at some point of space there is some accumulation of current which is going to violate your conservation law. So this would have been violated had Jx really been a function of x. So now therefore we can actually write down the general solution that can be built from the basic solution that we have written here. This is the basic WKB solution, and we can apply this to two different regions. One is classically allowed region, that means where I have E minus Vx to be positive, and there we know p square can be written as h bar square k squared, with k of x always positive. So I can write down, just by looking at this solution of psi of x, as psi of x is equal to some constant, say a bar, divided by square root k of x into exponential I, that h bar gets cancelled with h bar k here, dx prime x0 to x. This is the first term, but then you also have the negative term. So this is b prime by square root k of x into exponential minus I k x prime dx prime x0 to x prime. So this a bar and b bar are basically constants, and this includes that 1 by square root h bar factor also, because this was basically p. If you remember, here we had square root p, so I would have 1 by square root h bar k, but that h bar is being absorbed in this constant a bar. So look at this crucially, and you can see that the first wave, which has a coefficient of a bar, moves to the right, and the second wave, which has a coefficient of b bar, that means this one, moves to the left. How can we actually figure this out? You can figure this out simply by recalling that the energy eigenstate psi of x, which we have written here, this is accompanied by the time factor, which is given by e to the minus iet by h slash, which is already there in the stationary state solutions. So when forming a full solution of this Schrodinger equation, you also have e to the minus iet by h bar. But then from looking at this argument of e to the minus iet by h bar and then e to the ikx, you can figure out in which direction this is moving. Similarly, here we had discussed about classically allowed region. If you now look at classically forbidden regions, you can immediately have p square as minus h bar square kappa squared, and this implies our p of x is I h bar kappa of x. So just like the previous case, we can write down my general WKB wave function, some constant divided by kappa of x into exponential kappa x prime dx prime x0 to x. Similarly, we will have d bar by square root kappa of x exponential minus x0 to x kappa of x prime dx prime. Now the argument of this first exponential, which I have mentioned here, it grows more positive as our x grows. Okay, so first term is basically an increasing function as x is increasing. Similarly, by the same argument, the second exponential here becomes more negative as we grow x. Therefore, this second exponential or second term is a decreasing function as x grows. Now in pH 204, you had always encountered constant potentials to start with, and therefore your kappa was constant, and you obtained this e to the power kx and e to the power minus kx only as the solutions. But here you can see that there can indeed be these integrals there. So let me stop here today. In the next class, we will discuss about something more, some more tricky ideas and tricky concepts about WKB solution.